Okay, so today is the last topic for the midterm. I'm going to tell you how to find the inverse of a matrix, which is kind of an interesting topic. So, and as I mentioned, on Wednesday, what I'll do is like a review session. I'll send everyone like an announcement telling you which problems I was planning on solving. So that way, if you want, you can think of them before coming and you know, not just like watch me like answer them. I will record it anyways, that class. So. Let's see. So, yeah. Yes, instead of the lecture, yeah, it will be during class time then. There's not that many topics in this class, so we do have extra time. It's more important to get this like the start the semester well, with make sure everything is covered. So, because yeah, actually, it's not. We kind of already went through like the thing that gets a little bit most time to get it used to, which is like how to do the matrix multiplication and all this stuff. But after that, like many things just follow very quickly. So okay, imagine I had given you this matrix, right? Maybe this is like a matrix that appears like when you're solving a system of linear equations, right? So far, we have when we have been solving systems of linear equations, we have been simplifying the matrix using row operations, right? So what we're going to do for now is like take a different perspective on what these row operations mean. So again, what could be what's the goal like of applying the row operations is to try to get as close as possible to the identity matrix, right? So in this case, I mean there are different ways to start this, but one option to get to the identity is to just swap the first row with the second one to get like the one already in the beginning. I mean you could also have divided this one by 1/2. That's up to you, but let's do it this way. I'm going to exchange row 1 with row 2. And you do that, you get 1, 2, 2, 6, right? So, okay, this looks good. And then I will use I need a lot of space. Put a 0 here, right, which is the next step. You can do minus 2 times row 1 added to row 2 and substitute that into row 2. And now you get here. Okay, let's see. Oh, but this is before and keep going on. I should emphasize this. So when from going to here, right? From this one to this step, we swap the rows. You should think about like that operation is something I had mentioned before, but just to emphasize it. This is like a reversible operation in the sense that you can take this matrix and return to the original one, right? How can you go from here to here? Well, in this case, you do the same swapping operation, right? If you swap row 1 with row 2, you get back to where you started, right? So these row operations have a property that are kind of like you can always like change your mind and undo them, right? So for example, from here to here, you're doing minus 2 row 1 plus row 2. But imagine you had started with this matrix, right? How will you get back to this one? What operation could you do to go backwards?
2 times row 1 plus row 2.
Yeah, so you could do 2 times row 1 plus row 2, and that would give you the original one. And that the choice of 2 is useful to notice that here you were doing -2, and then you have to do 2, use 2 row 1. So it's kind of like the opposite, right? Like 2 and -2 are opposite. So to go backwards, you're kind of choosing to do the opposite operation. Okay. And so the last example of like row operation that we needed to use in general was like to divide by a row by a number. So in this case, like to put up 1 here, you do 1/2 row 2. And well, maybe this is the easiest of all to see, right? This is also reversible in the sense that you can start with this matrix and go backwards. In this case, what's the reversal operation? It's just multiplying the second row by 2, right? If you multiply the second row by 2, you get back this one that you started with. And so 2 and 1/2 are also kind of like opposites of one another, right? So what I'm trying to say is that if every step connecting these matrices is reversible, and kind of like what the reverse version should be is kind of clear from the operations themselves. Okay, and then just to finish this up, the last operation we can do is -2 times row 2 plus row 1 into row 1. And if you do that, you get 1, 0, 0, 1. So we ended up at the identity for this particular matrix. So far, so good. Any questions up to this point? Okay. So now what we're going to do is take a slightly different point of view, which is useful for this stuff about finding the inverse. So this is like the only time I will do this. Like it's not like how I'm expecting you to do this in practice, but it does give you like some insight that you cannot see just if you write the operations in terms of the rows. So my point is that instead of thinking that you're doing like, for example, like the swapping of rows, what I'm going to say is that there's like this is equivalent to having done like a matrix multiplication, which is not so obvious, but we can think about it for a second. So like you may remember this diagram from the beginning of the semester. This is also why I started with matrices at the beginning, so this would become more natural. So you may remember this diagram. Before in my diagrams, I would feed a vector into this, but I mean, actually, there's nothing preventing you from feeding a matrix if you want into this as well. So what the process that's going to represent this exchange of rows, right? It's going to be this operation when it takes place on the identity matrix. Okay, so if I'm going to replace row 1 with row 2, if you do that to the identity matrix, right? If you swap row 1 with row 2 of the identity matrix, you get something like this, right? You just flip those. And my claim is that this matrix times that matrix, what happens if we do that product? Well, if you do this product, you get 0 with 1, it gives you 1, 0 with 2 gives you 2, 1 with 2 gives you 2, and then 1 with 6 gives you 6. Okay, so what I'm trying to say is that instead of thinking, well, you're just exchanging the rows, right? An alternative to thinking about it in that way is like, well, we're not this exchange the rows operation is actually the same as having multiplied by this particular matrix. Okay, so this is why at the beginning of the semester I also was asking you, well, let's find a matrix which sends like a vector xy to the vector y-axis. If you remember, like this switch matrix that we had discussed for a while, like all these matrices that do like funny operations on the vector, there's also like kind of the work as well for if you feed matrices into that. So what I'm trying to say is that the effect of this operation is essentially having done this matrix multiplication. Again, this is not like a useful thing in practice to use, but it is theoretically useful for what you'll see in a moment. Okay, so now think of this as an input, right? That you're going to run through this process, which is minus 2 row 1 plus row 2. So now I'm going to feed this into a process, a new one. And what matrix do I put here? You will put the effect of doing this operation on the identity matrix. So if you do minus 2 row 1 plus row 2 in the identity matrix, you get, well, you're doing minus 2 row 1, so this becomes negative 2. And then the other one is 1. So this is like the matrix that resolves if you did this on the identity. And what I'm claiming now is that if you multiply this one times this one, sorry. If you multiply this one times this one, well, it's a product that you can check. You get 1, you get 2, you get 0, and then you get 2. And so once again, this matrix coincides with it. That making sense so far, so good? Just interrupt me. Let's keep going. So now I'll feed this into this operation, but instead of thinking it as a row operation, I'll think it, well, I'll feed it into a machine that will, what do I put here? You put the effect of doing 1/2 of row 2 on the identity. So if you do 1/2 of row 2 on the identity, you get 1, 0, 0, 1/2. So what I'm claiming is that if you do this matrix times the input, well, this one is easy. You get this, which is this thing, right? And there's one more operation left. Where we're doing minus 2 row 1, row 2 plus row 1 and substituting that into row 1. So if you do that on the identity matrix, you get 1, negative 2, 0, 1. So my last claim is that if you do this matrix times 1, 2, 0, 1, you get 1, 0, 0. Which is it then? So like of all that I have said is like the takeaway is like instead of like just having written down like do 1/2 of row 2 or like do this thing, this operation, any of those is actually equivalent to having done like a matrix multiplication. Okay, so secretly we were doing some matrix multiplication, so that maybe it was definitely not obvious from how I was writing it, but you like someone realized this for the first time. I don't know who was that person, and once you realize this, it's a kind of useful. Why? Because if you put everything together, that means that you started with the matrix 2, 6, 1, 2. Let me write it down here. What that means is that you started with the matrix. Or I think I have wrote that. You had the matrix 2, 6, 1, 2. The first process you applied was 0, 1, 1, 0, right? The second process you applied was 1, 0, negative 2, 1. And the third process was 1, 0, 0, 1 half. And the last process was 1, negative 2, 0, 1. Right? So what I'm saying is that this matrix times this matrix times this matrix times this matrix times this matrix is giving us the identity matrix. Right? And why is that useful? Because I mean this whatever this product is just some matrix P. I don't know what it is. Let's just call it P. And this was our matrix A. Right? So we're getting that B times A equals the identity. But what did that tell us about what the matrix B is?
The inverse again.
It is the inverse secretly, right? So out of nowhere we found the inverse. Like I'm about to write that like more like as an algorithm for you to like actually have like a working thing. But so this is actually saying that secretly this is like the inverse. Okay. So like the usefulness of like thinking of the row operations in terms of matrix multiplications is that kind of it gives you by accident or by providence like the formula for the inverse. Okay, so the algorithm for when is a matrix invertible is like if you can reduce this and you get to the identity, the matrix was invertible. And by the way, the inverse is essentially the result of applying the row operations on the identity matrix. So it's kind of like gives you everything you could have asked for. Okay. Not making sense. I'm about to write this, but it's kind of like cool to see that that's how it ends up happening. So let me see where I can put it. Like I think I have A is invertible when you can get to the identity matrix after applying the row operations. That's how you identify whether when a matrix is invertible or not. So A inverse exists when you get to the identity matrix using the row operations. And to find A inverse, we do essentially what we were just doing. So to find A inverse, what you do is like you take A augmented with the identity matrix, and you will, since multiplication in this case corresponds to the row operation, what you can do instead of like doing that product, because doing multiplications of matrices is it's kind of tedious even for 2x2 matrices. So you get the row operations. And the idea is like A, if this was invertible, the left-hand side will give you the identity, and whatever you end up finding here is going to be the inverse. I'm about to do it in this example so that it's more, you get like a better sense of what I mean. But essentially, we just reduce the matrix as before. It's just that in addition to reducing the matrix A, we kind of apply the same operations at the same time on the identity matrix to see what's the effect on the identity matrix. So it's kind of like adding like two more like, a vertical line together with the identity. And I'm about to do it for this matrix so that you see how this looks like. It is actually very cool. So let's how this looks. So my claim was like, if you want to, let me erase it. I still want to be referring to this. So what I'm trying to say is that to find the inverse for this matrix, you would take the matrix itself. you take that matrix. 2, 6, 1, 2, augmented with the identity 1, 0, 0, 1. And now apply these same operations we just wrote, but like to both at the same time. That's basically it. So like the first operation was this swapping thing. So when you swap rows 1 with row 2, you get 1, 2, 0, 1, and then 2, 6, 1, 0. So again, it's what we had before. It's just we're also doing seeing the effect of the identity. It's like the only thing. Then you do -2 row 1 plus row 2 into row 2. And well, we already knew what happened here. You get 1, 2, 0, 2. And then when you do this operation here, you get 0, 1, 1, -2. Okay. And then you do this 1/2 of row 2, which is actually kind of easy. So you get 1, 2, 0, 1, and then 0, 2, 1/2, -1. And just one more to go before we're done. If you do the last operation, which is -2 row 2 plus row 1 into row 1, that means that this is 1, 0, 0, 1, which is the identity, right? And then here you have -2. So here we got to the identity. So my claim is that whatever else this is the inverse. That's basically it. So there you go. That's the inverse for this metric. So this is a. Now let me write it down more explicitly. In other words, A inverse is -1, 3, 1/2, -1. And how do you can always check, because literally if you were to do this, in other words, like my claim is the product of these 4 matrices is literally this matrix. Like if you were to do it, it's just like doing 4 matrices multiplication is like very tedious. You don't want to write it as a product. So the alternative of writing it as a product is just to keep track of how the operations end up affecting the identity. So this thing, it equals that thing. So this is the same as this. So if you were to do this multiplication with this matrix, you will get the identity matrix. That making sense? And that's more or less it, like regarding how to find inverses, like for matrices. This is literally what you always do. What I'm about to do just for the remainder of the class is do a little bit like more interesting examples so that we get used to it. But it is like this algorithm, like kind of like notice that this method is giving it's like killing two birds with one stone, right? In the sense like if you happen to get to the identity, right, it also spits out the inverse for you. So like you're doing like you get 2 things at once. If you only wanted to know for some reason whether the matrix is invertible or not, but you don't care about what the inverse looks like, then there's a thing called the determinant, which we'll do after the midterm, which will tell us, oh, this matrix, you find the determinant of the matrix, and this will tell us whether the matrix is invertible or not. It would be a number basically. So it's kind of like but if you want like the inverse at the same time, like this is kind of like a convenient method to use. Okay. So yeah, let me do like this can take a little bit of time. So let me do like the one that is very important, which is like the general 2x2 case. Yes.
I think you might have to divide the second row, the third operation into 2.
Here?
Yeah.
Oh, yes, you mean that there should have been a one here?
Yeah.
Yes, if there should have been a thing. Which is what we had on top, correct? And since I was just copy pasting things. Okay, anyone else? Okay, so this is also useful to do. Let's do the case of the inverse of a matrix. Which we just know is A, B, C, D, so. So now I'm working with a 2x2 matrix. I don't know the entries, I'll just call the entries A, B, C, D. Okay, and let's try to find like a formula for what the A inverse should be. This formula actually does reveal some useful things, so that's why it's useful to make it in the general case. Okay, so again, like the idea is like if you want to find the inverse of a matrix, you have to augment that with the identity. So you put like A, B, C, D, right? Augmented with identity matrix. Okay. And now the question is, what do we have to do here to get to the identity? What are the steps that need to be done? So what could you do here to get to, what's the first thing we should try to put? Like we should try to put like a one here. So what could you do to get a one here?
Multiply the first row by the inverse of that.
Yeah, so you want to do something like 1/A, row 1, right? I agree with that, but we have to be careful about something, right? So what's like the thing that could go wrong? Right, like A could become 0, right? So like we have to at least think about what happens if A is 0, right? So before going on, continuing, I mean, at some point you can either work with this, like ignoring that, or like you just like on the side think about what happens if A is 0, right? So what happens if this is like a subcase or case A equals 0? So if A equals 0, you get like 0, B, C, D, 1, 0, 0, 1, right? Correct? And now, if you want to put a 1 here, it cannot be through this 0, right? We need the help of the entry C, right? So because like you would like to swap the two rows, right? To put like a C on top and then do 1/C, right? Multiply by the inverse of C. But that actually kind of puts you in the same spot, right? Like so like what I'm trying to say is that this actually has like too many cases as well. What happens if C equals 0? Well, if C equals 0, you get 0B, 0D. And my claim is that this is never invertible, right? Because the first column already is full of zeros. You can never get like a 1. We need to reach the identity, so we cannot get a 1 here, right? So this is not invertible. Since the first column is full of zeros. Does that make sense? And again, the idea is like it is invertible if you can get this to look like the identity matrix, and it won't because of the first column. But if Z is not 0, right? Then you can do 1/C row 2. And if you do 1/C row 2, you get 0B 1 D/C 1, 0, 0, 1/C, and this thing, will start looking very much like what I'm about to do. So this will be very similar to what I'm about to do. Okay, so it will be similar to this, which which can be dealt in a similar way to be analogous to what I'm about to do. So when z is different from 0, it's not that different from what I'm about to show you. So I'll just do it for a non-zero, but it's more or less the same idea. But like the reason why I wanted to do this example is just to give you like a sense of how you have to start breaking into cases if you don't know like the exact values of the entries, right? So when you do the row operations, like it sometimes may require some further analysis based on whether you can divide by a number or not. Okay, so don't lose track of the cases because you will lose information if you just like start dividing like and don't even think whether or not you're allowed to divide. That makes sense. So if we do 1/a/1, we get you get 1 b/a, then you get 1/a, get 0, and you get c b 0, 1. That's what you get when you do that operation. Okay. Now the goal, since we already have a 1 here, the goal is to put a 0 here, right? Just to do the first column look like the same as the identity matrix. So how do you put a 0 in this entry? What operation can you do to get a 0?
Minus c times row 1.
Mm-hmm. Good. So you can do minus c row 1 into plus row 2 and substitute that into row 2, right? Notice that here it is not important whether or not z equals 0, right? Because if z equals 0, then you're doing nothing, right? It's like leaving the entry untouched. So it is fine to have c equals 0 here. It doesn't require like further like thinking about what's going on. So that's okay. So if you do that operation, you get a 0 here, and then you get b, and you're subtracting c times b/a. Okay. And here you get minus d/a. And then here you get a 1. Is that making sense? So before doing more row operations, it's better to rewrite this a little bit so that it doesn't look too messy, like specifically the last entry. So I'll just like combine these two numbers, like put like a common denominator. So 1/b/a 0, and then this looks like ad minus bc. Okay, and then you get 1/a. So this is not, I mean, again, I'm not doing any operations here. I'm just rewriting the last entry of the matrix. Is that okay? But the way this number that appears in the numerator is what's called the determinant of the 2x2 matrix. So it kind of appears out of nowhere if you haven't seen that before. But again, like that, I'll tell you all about the determinant after the first midterm. So it's nothing to worry about. But this is kind of like you see it show up if you have seen that before. If you have like taken like a physics class where you do the cross product or things like that, you use the determinant formula. So it kind of appears naturally in this process. Okay, but now the idea is to put like a 1 here, right? So what do you do to put a 1? What's the operation that you have to do? Yeah, good. So I'm going to multiply by the inverse of multiplicative inverse of that. So I'll do A over AD minus BC rho 2. And am I allowed to do that? I'm allowed to do that provided AD minus BC is non-zero, right? So you can do this if AD minus BC is non-zero, right? If that happens to be zero, what happens if this is zero? If AD minus BC equals zero, you get 1, 0, 0, B over A, 1 over A, 0 minus A over A, 1. And this again can never look like the identity, right? Because now you have a row with a bunch of zeros, right? There's no way to make this become the identity. So this one, this can't be made the identity. This cannot become the identity, so this case actually is not invertible. So in fact, when AD minus BC is equal 0, you cannot invert the matrix. That's actually the condition for, I'll tell you again after the midterm, for invertibility of a matrix, the determinant has to be non-zero, basically. So can't make this identity. So no inverse. But again, under our assumption that this is non-zero, then you can just keep working. You do that operation, this cancels, and then when you do this here, the A cancels this A, right? When you do that product, you get minus C over AD minus BC, and then you get A over AD minus. Is that making sense? And we're almost there. Only one more row operation needed. So the last step is I want a 0 here. To get a 0 here, I should do minus B over A, right? Row 2 plus row 1. So let's put it here. So I want to do minus B over A row 2 plus row 1 and substitute that into row 1. If you do that, then this gets 1, 0, 0, 1. So that's great. Like whatever we have here will be the identity. And sorry, the inverse. So if you do that, you put like okay, let's see what we get. When you do B over A, when you do B over A on this entry, let's start with this one because it's easier. There's an A here. So this A cancels that A. They cancel, so you just get in the numerator minus B over AD minus BC. And when you do B over A on here, right, you get 1 over A. There was a 1 over A from the get-go, so like there it is. And then you do minus, oh, there's a minus here with a minus here becomes plus, so you get plus BC over AD minus BC. Is that okay? This is the inverse. This is the formula for A inverse. But it's not usually that way. I mean, it is fine, but it can be made to look better. To do that, you just have to work a little bit of what this is. So what is 1 over A? Let me write it here. So what I'm saying is that A inverse is going to be that, but what is this thing? Oh, again, you can do like common denominator, so it's like A times AD minus BC. And when you do that, you put AD minus BC on the top, plus BC minus B over AD minus BC minus C AD minus BC. And then A divided by AD minus BC. Okay. And it doesn't look that much better, but it is because this BC cancels that BC, right? So you get AD over, you get just AD in the numerator, and there's an A that cancels this A. So this is the same as P over AD minus BC minus B over AD minus BC minus C over AD minus BC and A over AD minus BC. Is that making sense? What do you notice? That it's a bunch of fractions, right? And every denominator is exactly the same, it's AD minus BC. So you can take it out of the matrix, and the way in which usually the formula for that inverse is written down, which is more compact, like looks a little bit better, is that the inverse of AB BD is 1 over AD minus BC times the matrix D minus B minus C. And that's the formula for the inverse of a two-sided matrix. Okay, which is this one, you just take out the denominator and move it to the front. Is that making sense? And it actually works. It does work for the matrix we had started like at the beginning of the class, right? So if you follow this formula, what would be the inverse of like 2, 6, 1, 2? I believe that's the matrix I had given you, right? Which we started with. Well, it's 1 over AD minus BC. That, again, this would be called the determinant, so it's 1 over the determinant. So it would be 1 over AD becomes 4, BC is like 6. So 1 over 4 minus 6. D is 2. B is negative 6. I mean, B is 6, so it becomes negative 6. Negative C is negative 1. And A is 2 also. So this is negative 1/2, 2, negative 6, negative 1, 2. And you can put this negative 1/2 inside, and so you get negative 1, 3, 1/2, and negative 1. Which hopefully that's how it looks like the inverse we have found. So it is like a special case of this more general formula. Is that making sense? Yeah.
I feel like I'm missing a step somewhere to see where you got 1 over A, it's BC over AD minus BC. You did the operation negative BA
Here.
over A, yeah, that one. And you did negative B over A or 2. I'm trying to find where the A went, and then it canceled out.
Oh, okay. So we were here, right? Let's start here. To put like a 0 here, right? I do minus B over A rho 2 plus rho 1, right? So this gives you the identity, right? Is that okay? And then I did nothing to rho 2, left the same, right? Then it's just easier, you're doing minus B over A. So when you do that here, the A's cancel. That's how you end up with this entry, right? And then like here, this one already had like 1 over A, which is the one that you see here. And then you're multiplying B over A times this, right? So you get BC over AD minus BC. Oh, and then let's see, you're saying that I'm forgetting like
The denominator, the A.
right, okay, let's see. Perfect. Yes, let's see if this is okay. Okay. Yeah, there's a good, perfect, excellent. And actually it was fine here because when I do common denominator, if like the common denominator would be yeah, good catch. So it should have been an A here. And the common denominator is still AD minus BC, and then it does give you, yeah, it's still the same, it is fine, but it was missing an
Want to make sure it wasn't good.
no, you were good. Just that I had done it in the previous class, so I already knew what it had to look like, but perfect. Yeah, I mean, this is like again, it actually goes back to the general philosophy of this class, which is it as individual operation is not bad because it's just like literally adding, subtracting, multiplying, or dividing. But you have to do this so many times, right? Even a single problem, maybe you have to do this 20, 30 times, right? That just increases the chances like for like a random like mistake happening somewhere. So it is like, it is a double-edged sword of like linear algebra, like where like the operations themselves are not that difficult, but they're just like happening over and over and over and over again. That like even like something easy when you do it multiple times, even the best player in whatever soccer or whatever sport you want, like from time to time, like probability theory will like get like will do like something that looks like amateurish, right? So it's just like we're just running this experiment trial many times, right? Which is kind of like how the hope behind like like Las Vegas, right? That if you play, eventually you defeat the house or whatever, right? If you do it millions or trillions of times, you will. But because like random events can happen. But so just be right. It is useful to double check your work after each step to make sure like it doesn't screw over the stuff, especially if it happened at the beginning. If it happens here, you kind of can fix it easily. But if it had happened from the very beginning, then you have to start changing one of. You might as well just start from like. You can bring a pencil, by the way, if you want to the exam. I don't mean you don't need to use pen or an eraser. I think it's kind of better because of this reason. It's just like the exams will be. I will scan the exams after you take them, so like it's kind of no issues with like if you later need to ask for a regrade or whatever, it doesn't matter if you use pencil. Just try to make like use a pencil that you can still see very clearly what you were writing. Let's see. Okay, so this is, I mean, it was a cool case just because it does give you like the sense of how the inverse formulas look like. They more or less have like a similar format for any size. Yeah.
Is there any reason why A minus BC will be zero if the column vectors are linear?
Well, I mean, let's see, not from it is like a chicken or egg question. Like what we will do after the exam is that you can define the determinant as the volume or the area of a parallelogram whose vectors are like the columns of the matrix. So from that perspective, when what happens is that when the vectors are like a one column is like a linear combination of the others, like it just like the thing collapses to something of smaller size, so it has no volume. I mean, I'll explain it once we get there, but from here it is not right, it's not clear. But once we get to that point, I'll tell you. It also depends a lot on, again, how you define the determinant, like in the first place. Like there are many alternative ways to do it, but I'll define it in terms of some area. So from there, it's kind of more clear. But yeah, it's nothing to worry about for the midterm. Like finding the inverses, yes, but like what's the meaning of this AD minus BC? Like it's just like a thing that appears. So yeah.
How many questions will involve this sort of calculations on this test? Like,
Well, inverse, I wouldn't put more than one problem. Now when you reduce, like, I mean, at the end of, like, it does look longer because, like, I didn't give any num value to any entry, right?
yes.
But by operations, you mean like reducing the matrix? Well, that kind of like that will appear in a couple of problems just because most problems are literally just that. But I wouldn't put anything that it has like so many very unknowns, like for lack of a better term. Yeah. In fact, the next one is kind of more realistic. The one that I was going to do, which is like a 3x3 case, but it is less tedious because there's only two letters, A and B. So let's do that one. But yeah, like it won't it should be doable within 80 minutes. So yeah. Okay, let's finish like with this example. And as I said, I don't know if I already said it at the beginning of class, I think I did. Once I'll do like a review session, I'll send you like an announcement with the problems that I plan to solve from this PDF. In case you want to take a look at them before the review. Okay, so here's another example. Let's try to find the inverse. The inverse of A0, A0, B0, A minus 1, 0, A minus 1. Okay. That one is actually better than this one because there are just 2 letters instead of 4 and a couple of zeros. So it's actually, it won't be that bad, you'll see. This is more in line of what the sort of problem that I expect you to be more comfortable with. It's not that this one is bad per se, it's just like takes a lot of time, you know. The level of difficulty of these problems is always like, how much time do you spend like doing like all the arithmetic? Because like the algorithm itself doesn't change, right? Like you have to do exactly the same regardless of the situation. Okay, but so again, the idea is like if you wanted to find the inverse for this matrix, you have to augment it with the identity to put A0, A, 0, B0, A minus 1, 0, A minus 1. I put 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. So what's the first thing you can do here? It's kind of similar to last time, right? What's the first operation? Again, the goal is to get this to the identity, right? Yeah.
First relate.
Right, let's do 1 over A as before, right? So 1 over A rho 1. And again, at some point you have to say what happens if A equals 0. You have to analyze, it is expected that you analyze at some point like that case. So what happens with the case A equals 0? If you look at that case, you end up with 0, 0, 0, 0, B, 0, negative 1, 0, negative 1, right? And that's already bad enough because the first column is a bunch of zeros, so it cannot work, right? So this can never be, like you can't have a column with a bunch of zeros, there's no way to get a 1 there. So can't happen, or it can get this to, can be invertible. Since we can have a column full of zeros. Does that make sense? So if you do 1 over A rho 1, you get 1, 0, A minus 1 over A, 0, B 0, 0, sorry, A 0, A minus 1. And then you get 1 over A, 0, 0, 0, 1, 0, and 0, 0, 1. Is that making sense? So, what's the next operation we can do?
Multiply row 1 by A or negative A.
Yes.
And plus row B.
Good.
Onto row 3.
Perfect. So we can do minus A rho 1 into row 3. And by the way, eventually we'll need it. We can also do 1 over B rho 2. It will be needed and it doesn't affect anything else. So let's do also 1 over B rho 2. And again, you must think what happens if B equals 0. So case B equals 0 can't work actually because if B equals 0, you would have the second column full of zeros, and that also is not allowed, right? Can't work. Since the second column would then be full of zeros. And this can't happen. Is that okay? Is that making sense? So, if you do these operations, you get 0, 0, a minus 1 over a, 1 over a, 0, 0, and then you get 0, 1, 0, 0, 1 over b, 0. And then this one becomes 0, right? Then you have a 0 here, and then we're doing minus a row 1. So when you do minus a row 1, you get a minus 1 that was from the beginning. Oh yeah, I should have put let's see if let me see if this was if I had to change the coefficients. Let me check. Yeah, I did it in the other class, so I still remember it. Oh, okay. It is like this is the one that I wanted to do, but let's put like a minus a here. Sorry about that. So there's a minus a here. So nothing else has been affected except now. So instead of doing minus a, I'll do plus a. Perfect. Now it will work. So sorry about that. It looks the same, 0, 0, but now because it's plus a, this cancels the a's, and then you had an a minus 1, you get 2a minus 1. That's what I was going for. And you're doing plus a, so you get 1. So again, please stop me. Yeah.
So if there wasn't a minus a there, then the matrix wouldn't be invertible.
I think that's what it was going to. Yeah, because you ended up with a 0, right?
Well, you could just subtract row 1 and row 1 from both here, and get 0.
Right, exactly. Yeah, that's right. Yes. Good catch from the very beginning. Like, yeah. Yes.
Would there always be like different ways to solve these problems? Different
Well,
orders to do the R plus, cause like
there's a little bit.
personally, I find myself doing different ways or like different orders. Like I would have canceled out the A's first. Like that bottom A is just bothering me. I wouldn't have divided by A over 2. Like I would think maybe to do that one first.
You can do that.
Like-
I mean,
Like, will it work out for me on the test, basically, if I choose to do that?
I mean, in the sense, it will give you the correct answer. It's just that, well, it does, okay, when it's just like canceling, that's not. Doesn't make much of a difference in terms of time. It's just that sometimes, like, for example, how should I put it? Like usually, like the idea of why it's called like an algorithm is for everyone to try to start like in the same way, in the sense like, oh, you put like a 1 here and then but make zeros, right? And then a 1 here and then make zeros and so on. There are different ways to get there. It's just that if you choose other ways, like you may take a couple more steps, but it's not that your answer would change, you know, like it will give you the same answer. Like it, yeah, like okay, for example, just to say something very silly, maybe someone could have said, well, let me exchange rows 1 and 3, right? For some silly reason, and then just divide by 1 over a minus 1 over a, right? Like do like a, which is kind of looks very like, why would you do that? You know what I mean? But it's not that it was wrong. You could still do it, but it would take, you just gain yourself 2 more extra steps, right? So another thing someone could have done at the very beginning is again like do 1 over a row 1, 1 over b row 2, and 1 over a row 3, for example. Like that's also, I mean, there are a couple of variations. I'm just trying to solve all the problems essentially in the same way every single time, so that it kind of like starts looking more like a mechanical thing, that you stop thinking about how you should go about it. even if there's like particular examples where maybe like a slightly different version would have been faster. That way it's more like it's completely like a computer type thing, like you don't think and you just like make sure like you don't make any type
Okay,
more.
that makes sense.
Yeah,
In the last version of the matrix on the third row, third column,
this one.
yeah, how did you get to that?
Oh, perfect. So we're doing plus A row 1, right? So when you multiply this by A, right? The A's cancel, like there's an A in the denominator that cancels that A, right? So you get A minus 1 here. And when you add it with A minus 1, you just get twice A minus 1.
Okay.
Is that making sense? But yeah, it's kind of like the observation that he was making, like in the sense like I needed like a minus here to not make it like a silly problem, because if the two rows were the same, like then you can just subtract them all together and you would have had 0, 0, 0, and that also could not have happened. So that's why I had to change one of the letters. Sorry, one of the signs. Again, like once after the first midterm, once I give you like all these rules, all this determinant thing, let me see if many things just become more clear than how I'm doing it, but right now. And we're almost there. So the next step is that I want to put a 1 here, right? To put a 1 here, I have to do 1 over 2 A minus 1. That making sense? So and again, that can only be done if A is not 1, but A equals 1 messes everything up, right? Because it's the same 0, 0, 0. That cannot happen. So like again, you just make a remark, case A equals 1 doesn't work. So you would get like a row full of zeros. Since you would get. So it's basically game over once you get full of zeros as a row or full of zeros as a column. Either screws over the process because the identity matrix has at least a 1 on each zero on each row and on each column. Yeah.
Oh.
Sorry.
All zeros. Let's see.
Oh, k equals well. I was thinking about this row, but also you can think, and also you would have had like the third column full of zero. I mean, that's many different perspectives. Also like a column full of zeros. You can put it. So it either would have counted as valid. Like what I'm trying to say is that it's not just like the rows that could go wrong. Once you have a bunch of zeros in a row, once you have a bunch of zeros either in a column or a row, then there's nothing else. Like you're over because like identity matrix always has at least a 1 on every row or column. Is that okay? And okay, now this is not too bad. You get 1, 0, 8. We're almost done. This one. So you get 1 over 2 A minus 1, 0, 1 over 2 A minus 1, 0, 1 over B, 0, and then 1 over A. 0, 0. Okay, so one more step, and whatever we get is equals. And it's just that we need a 0 here, right? To get a 0 here, you just multiply by the inverse of that. So like let's do minus A minus 1A row 3 plus row 1 into row 1. And that will guarantee the identity on the left hand side. So you get 1, 0, 0, 0, 1, 0, 0, 0, 1. And what happens with the first row? Well, let's copy first like the other two that are unaffected by this. So when you do that, what happens? Like when you do this operation, this A minus 1, if you see it cancels this A minus 1 here. So you get minus 1 over 2A. You get a 0 here. And there's something similar that happens here. It's like 1 over A minus 1 over 2A. So that actually gives you 1 over 2A if you do the algorithm. So that's like the formula for A inverse.
You know how you examine all the cases when like A equals 0,
Mhm.
B equals 0? Like, can you just do that all at the end? Cause then like the denominator.
Okay, right, it is, see, the thing is like. You kind of see it here, it could be that, say you have to do a case, but it's not shown explicitly in this version because maybe, when you were simplifying, you do some extra cancellations and like, I wouldn't go as far as, I think it's, I mean, you can definitely use this to double check whether or not you went through all the cases. But it could still be that, I mean, as a principle, like that maybe, case equals 2 was something that it had to be considered, but somehow it's not, I mean, it is, okay, it's true, in the end, it's kind of always reflected here, but it may not be so explicitly reflected because of how you write the, like, because there's so many fractions involved and things like that, maybe you could rewrite it in a way that is less clear whether like, there was an extra case to be considered or not. So I would be like, I'm not saying, okay. I'm not saying that you have to, while you're solving it, yeah, this is kind of what you should pay your most of your attention to, right? So at the end of the day, you can just like, on a corner of the problem, you just like keep track, oh, I have to use A equals 0. I mean, I have to look into A equals 0, B equals 0, or A equals 1. And then at the end, you can say, well, neither of these cases work because you get like a row or column full of zeros, and that's fine. So you don't have to be stopping along the way, if that's what you mean. You just have to, but you just keep track of what assumptions you were making. Which again can be corroborated against the inverse formula, which is what you're saying, but it's better still, I would still write them down somewhere.
Could you reiterate how you got 1/2A?
Oh, right, like this one.
Yes,
So the thing is like, okay, let's see if this one I did well. It would have been 1/A, right? There's a 1/A here. But when you do this operation, right, you're doing minus 1/2A. And then when you do common denominator, this hopefully should be 1/2A. Is that better? Yeah, well, thanks. Anyone else? Okay, so this is more like along the lines of the inverse formula that you should be kind of like comfortable with like where that's maybe like 2 parameters. They're not, I mean, once you get used to it again, like you can sometimes combine like different. The thing that takes a little bit of time is that like you have to do this copy paste, copy paste, copy paste, like the matrix with this augmented version, right? Like that's where like you spend some time, but like sometimes like you can combine like do more than one row operation at the same like on the same step and things like that, and that will save you a little bit of space. So that's kind of it's keep track of. Is that making sense? So just before we finish, to show you something quickly, because I wasn't sure if everyone had paid attention to this. If you go to the, let me see if I can share my Canvas side. Firefox. Yep. Now I have to log in. I don't know why I did this. It's so silly. Okay, let me log in again, and now I have to do this authentication things. uh, Make it this one. Oh, okay, it was not needed for some silly reason. Okay, so what I was going to say is that if you go to the mirror site, right? For example, if you click on assignment 1, that's where I'm posting the solutions of the assignment. So on the same, like where I'm writing the instructions for the assignment, if you click on it, you'll see the PDF with the solutions. So there's one more assignment that was due this week. That's assignment 3. So after, like, I don't know, when was it due? Like maybe Thursday, I believe. So after Thursday, I'll post the solution to that one. And all of these problems were taken from this math 250 problems list. So like on Wednesday, the review, I'll choose some from there. I'll send you like an announcement in a couple of hours, depending on how many people will come to my office hours, telling you which ones I was planning on doing. And then beside that, as I was saying, like for the midterm, just pay attention to those problems in the PDF. Plus the Canvas mini quizzes, which are a bit more computational anyways. So like these problems on the PDF are more important, but just make sure like that you understand the example done in class, plus this PDF, plus the Canvas quizzes, and like again, the exam will be fairly, relatively similar to that. So just like that. Yes, I'll see you on Wednesday unless you want to come to the other side.